Good evening. My name is MattBoden, and this is my MSGIST capstone project presentation of an NDB or NBR and NDVI study on vegetation health and recovery after the Mendocino complex fire. Here's the agenda for the presentation. We'll briefly discuss the study area, objectives that I want to answer, the model used to process the data, what data was needed for the project, the results of the analysis, and finally, any questions that you may have. The Mendocino National Forest is located roughly 90 miles northwest of Sacramento in the coastal mountains of Northern California. The Mendocino Complex Fire was started on July 18, 2018, and burned for 2 months. And at the end of September, it was finally 100% contained. Even though crews had to battle intermittent flare-ups until January of 2019, it approximately burned 459,000 acres. The fire was comprised of 2 separate fires, the ranch and the river fire. The ranch fire was obviously the bigger one and burned over 410,000 acres, which is roughly 90% of the study area. Here are the objectives of the study. How significant is the change from the pre-fire vegetation health? Which ground cover class or classes observed the highest post-fire loss and recovery rate? And has the spatial pattern remained the same in the studied area, or has it changed? Here's the data that I needed in order to complete my study. I downloaded Landsat 8 30-meter imagery from the United States Geological Survey's website, Earth Explorer. I used 6 separate images over the course of 5 years. I focused on using only the bands I needed to create the NBR and NDVI images, which were the infrared band 4, infrared band 5, and the shortwave infrared band 7. Finding images with little to no cloud cover proved hard since the month following the fires contained California's rain season. It wasn't until May that the imagery had little to no cloud cover. So I tried to keep those images around the same date to provide little seasonality difference in value, which also provided better results due to no missing data for cloud coverage of the study area. The National Land Cover Database, 2016 was acquired from ArcGIS Online Living Atlas through the Multi-Resolution Land Characteristics Consortium. I use this for the ground cover classification and focus on 5 different vegetation groups that the NLCD lists for the area, which are shrubland, herbaceous grasslands, deciduous, evergreen, and mixed forest. These 5 land cover types comprise of 95% of the study area. Sorry, I lost my place. The other 5% was a mix of barren land, developed land, water, and agricultural lands. I chose to omit those from the study area only because they provide little to no impact to the overall study. Control points that I used to extract NDVR or NBR and NDVI data to. I used 10 control points per ground cover type for a total of 50 in all. I used the NLCD to place control points over specific ground cover classes. I tried to evenly distribute the points to collect data from over the entire study area. However, I did run into some areas where there was no data collected. I just believe that was having too small sample size per vegetation class. Here's the model that was used for the project. I started with specific Landsat bands, 4, 5, and 7, and used the raster calculator to create the NDVI and NVR images. After I created all 12 of those, I clipped them to the fire perimeter to only give me the data inside of the study area. As well, then I also took the NLCD and clipped that to the fire perimeter as well to give me only that data. Next, after that, I took the control points and used the extract multi-value to points tool to extract the data from all NDVI and MBR images for the associated control points, and exported that to Excel for further processing. Next, I use the raster calculator again to calculate the DMBR, which gives the overall burn severity of the fire. And then I use that and the vegetation layers to create a map of the burn severity by ground cover vegetation type. Lastly, to the top of the image, I took the NDVIs and reclassified them and used the Esri change detection wizard to create 2 images for change detection post-fire and 2 years post-fire, as those provide the better results on classification or vegetation change. And here are the results. The MBRs primarily focus on bands 5 and 7. To identify, these are used to identify the burn areas. I'm sorry, I lost my train of thought. How to calculate the MBR, you take band 5 and subtract it from band 7, and then divide those by band 5 plus band 7. And the results give you a scale of +1 to -1. The larger than 0 values indicate healthy vegetation, and values of 0 to -1 indicate burn areas. Here are the NBR images that were created, and the mean values of each are, the pre-fire one had a mean NBR value of 0.18. The post-fire had the lowest NBR at a -0.354. Your 1 year and 2 year post-fire, the mean NBR values were a little higher for the first year at 0.007. And the second year had the largest growth in NBR value to a 0.10062. Your 3 year and 4 year post-fire, there wasn't really much difference in the mean values to indicate really no growth from year 2 to year 3. And year 4 had a slight increase to 0.1239 from years 2 and 3. So as you can see, each image, the vegetation gets healthier, and the burn area is really declining, so which indicates the vegetation is recovering and repairing. Our NDVI is used to quantify vegetation greenness and useful in understanding vegetation density and changes in plant health. Primarily, bands used are for infrared band 4 and near infrared band 5. I take those 2 and add them and subtract them together and then divide by each other. So gets you another +1 to -1 values. The larger the value, the greener the healthier the vegetation is, where the lower number indicates an inverse unhealthy vegetation and less green. A separate study in 2017 that I used in my paper suggested using the following classifications to separate the NDVI values to, which help them identify ground cover change and land cover change. In our study here, it identified dense and sparse vegetation and shrub and water fairly well, but it had a hard time distinguishing between developed land and barren land. You can see the classes in the break for the specific NDVI values on the right. And we'll get into the 6 NDVI images that were used in the study. Pre-fire NDVI had a mean value of 0.259. Our post-fire had the lowest at 0.104. And 1 year post-fire had jumped back up to 0.147. Again, year 2, just like the NBR, had a higher or had a larger increase to a 0.215, and year 3 had a slight decline to 0.213. Could have been due to the light rain season that year, and year 4 increased to 0.222 for the NDVI values. So year 2 again showing the largest increase. Sorry, and but we'll circle back to the reclassified NDVIs at the end of the results section. Use correlation. I use Pearson's because I exported my data to Excel, and that Excel default way when you use the Corel function to identify relationships. Pearson's also uses a +1 to -1 value to indicate the relationship, and since both of these indices use a +1 to -1 value, I felt that Pearson's should provide fairly good results for the correlation. So as you can see, this is the pre-fire correlation of the NDV or NVR and NDVI images, and the R² shows a 0.1292, which is a very low correlation. So it shows really that there is no relationship really at all between the two images. However, once we get into the post-fire NVR and NDVI and each subsequent year, there shows a higher, very high correlation between the two. So it does show that there's a positive relationship between the NVRs and NDVI to identify changes in vegetation and burn areas. And then our first year post-fire had the actual highest correlation between the two. So the R² was a 0.92. And then every other year was between that and the post-fire one at 0.8. So you see 2 years is 0.89, 3 years is 0.89, and 0.87 for 4 years post-fire. So each year shows there's still a very high correlation between the two indices. And then getting into the control points, we can see that there's a decline here in 2018 post-fire, which is expected due to everything being burned. So their values obviously drop, but then you can see the rebound year over year, and which all indicate that the forest and surrounding vegetation is in the early stages of recovery. Shrubland, though, has recovered the most in the 4 years to 91% of its pre-fire NVR and NDVI values. And same thing for all the other vegetation types. I think this in 2020 for the evergreen, I think that might have been some myth data, because that shouldn't have diverged like that. It should have been the same. So I could have had a data error there that I just didn't notice. And then same thing with the mixed forest. Burn severity index. In order to measure burn severity, I use the raster calculator to take the pre-fire NVR and subtract it from the post-fire NVR, which turns values into a decimal form, and you can multiply those by 1,000 and turn them into whole integers. But I chose to leave them as decimals for the burn severity index, because it really doesn't change anything at all with the index. The general idea of the burn severity levels is that you can determine the overall impact of forest structure and the surrounding area and be able to focus in on the hardest hit areas for post-fire response and recovery management. The United States Geological Survey uses 7 levels of burn severity, 2 levels of regrowth, low and high, an unburned, low, moderate, low and high, and a high severity burn. Of the 459,000 acres burned, the vast majority of the acres burned fell into a low to moderate low severity. Burn classification is roughly 360,000 of those acres into those two categories. Our burn severity by ground cover type, our grasslands account for only 5% of the entire surface area of our study area. However, 60% of their class was classified as a low to moderate low severity burn. Shrublands are the most populated ground cover type in the study area and account for 239,000 acres, and 87% of their area was a low to moderate severity burn. Deciduous forest is the relatively small in the surface area of the entire study, but 90% of their area was classified as a moderate low to moderate high severity burn, which actually is the hardest hit vegetation type of the entire study area. The lowest severity burns were evergreens at 67% were burned with a low to moderate low burn, and mixed forest was classified as a low severity burn over 83% of their ground cover. The evergreen forests were the least affected ground cover type. This could possibly have been due to their high canopies and it being a ground fire instead of high tree fires, but can't verify that without any field research. And then we have our chart here that shows the vegetation types and their acres burned in by burn severity level. Using Esri's reclassified, or using the reclassified NDVI images from earlier, and Esri's change detection wizard, I was able to create multiple analyses of vegetation change across the study area. Looking at the two map frames, the left shows change from pre-fire to post-fire, and we see that the pre-fire shrubland and sparse vegetation dominated the landscape at over 85% of the study area. Post-fire, considerable change into all classes. Landscape now is a majority of barren land and developed area. Again, I think this was, like I said earlier, was a little more misclassified. It probably should have all been barren land instead of developed land because of the having a hard time distinguishing between those two classes with that classification. And then 2 years post-fire, you see a recovery of over 300% for shrublands and sparse vegetation as well. So shrublands went from 60,000 acres post-fire to almost 230,000 acres. And same thing with sparse vegetation, went from 9,500 acres all the way up to 85,000 acres. And that is it. That is all I have. Any questions? Thank you for your time.